So the first thing we're going to look at is what the heck a tautomer is. And before we answer these questions, I'm actually going to draw out like the tautomerization reaction. And it's not a billion steps, so that's awesome. And we are going to start with a ketone once again, just like chapter 16. So we have the ketone, and the ketone has some lovely alpha hydrogens. The reason they're alpha hydrogens is because they are one carbon away from the carbonyl carbon, and that is called the alpha position. So we're going to have either acid or base, and right now I'm going to show you the base reaction. So let's say we have NaOH. That base is going to go in and take an alpha hydrogen. There you go, bam, bam. And all we did, steal a hydrogen, give it a negative charge. And now at this point, there's not really much to do. We're going to do some resonance because we know that oxygen holds a charge better than carbon. So let's just pass that charge along. End up negatively charged O. Have a double bond here. And we still have those two H's left over. Now this guy can actually take some of the H2O that we just made, steal one of those hydrogens, and it will form an alcohol. So I'm going to pause and give everyone a chance to like write it down. So this mechanism is not too bad, right? Thank you. I know it's a Monday. Okay. So we have the ketone name, that should be fine. But we have to name the intermediate and the final product. So the intermediate is called an enolate. And since these are resonance structures, both of those guys are called the enolate. And the final product, I was going to ask you guys to guess it, but it's written in the question, so it's fine, is called the enol. And this name is actually kind of not awful because it's an alkene with an alcohol, enol. And then the enolate is just an enol, and the ate suffix just means negative charge. So it's an enol ate. And I will. Can I imagine that sound? Was it real? Don't do that to me. So that means negative charge, and then this means alkene plus alcohol. So the relationship between the two enolate drawings is what? I said this before, but they are resonance structures. Exactly. So a lot of people will then be like, okay, well, the ketone and the enol are resonance structures of each other because, like, they have the same formula and everything. All you did was move a hydrogen. In resonance structures, can you move a hydrogen? No, the only thing you can move is electrons. So these actually have their own name. The relationship between the ketone and the enol is tautomers. Should have given myself more room, but. And overall, this reaction is called a tautomerization, which is written here. So you guys don't have to spell that out. Okay, how do we feel about this so far? I feel like there's a lot of like names and stuff, but overall, does it make sense at this point? Yes. Okay, cool. So let's go back up here. So what are tautomers? I'll give you guys like the definition. So tautomers are a pair of constitutional isomers that rapidly interconvert in acid or base. So I'm going to write like a basic version of that. Of isomers that rapidly interconvert acid. Yes. So going from the ketone to the enol is like an interconversion, we could say. So the big thing I want you to take away from this is that you have to have acid or base to make this tautomerization happen. And we kind of already touched on this, but the big difference between tautomerization and resonance is that a pair of tautomers, you actually do a reaction to move a hydrogen atom. Whereas in resonance, we have the free movement of electrons across, I want to say sp2, but it could also be sp3, so I'll just say across a molecule. Yes. Yeah, so you're going to change, not really like, when I say change structure, a lot of people are like, get tripped up and pick like the weird looking answer choices. But yeah, basically for resonance structures, you just move along an electron. For tautomers, you actually change the base structure of the molecule and the functional group. And then we already said this, but I'm going to write it down just in case. So the relationship between the ketone and the enol is tautomers, or we could call them a tautomeric pair. And that means the same exact thing. And that's most likely not spelled right, but that's the same as tautomers. everything fits. Okay. So how do we feel? Let's do like the 1 to 5 thing. So put up a 1, 2, 3, 4, 5. 1 is if it feels super duper awful and you hate it, and 5 is like, okay, I vibe with this. It makes sense. Cool. Okay. I'm okay with that. Not bad for a Monday morning. So any questions before we kind of dive even more into it? All right. So as you can kind of guess, I said this whole chapter was about enolate chemistry. Now we know what an enolate is. So a lot of this chapter revolves around first using a base or an acid to create the enolate. And then once we've made the enolate, we do something else. The first thing we're going to talk about is racimization. So I'm actually going to make, I'm going to make another page. And we're going to cover the racimization reaction. And the big thing with this one, this is where I lose a lot of students. So this reaction is not really like a whole different reaction, right? So I want to preface it by saying, when we did the tautomerization, right here, we said that it could interconvert, right? So it's not at equilibrium, but it can also go backwards. So I'm going to just draw this arrow saying that it can go backwards. And the reason I am pointing that out, sorry, I don't know why it's deciding to give me a 2. I'm going to copy this thing. And the first thing we're going to do for racimization is essentially just copy what we already had, because it has the same base reaction. The biggest difference is I'm going to draw it out linearly. So sorry if this is super ugly, but I don't want to redraw everything. All right. So this is the exact same reaction we just had drawn. All I did was move it around a little bit. So is this part okay? All right. So we know that it could go backwards. So if it went backwards from this point, we're going to add a hydrogen back here and kind of reverse everything, right? In this case, it would make no difference. Everything would still get the same answer. But what if we put a methyl group there? And replace that with, let's say, an ethyl group. I should have just redrawn it, to be honest, but that's fine. So what have we created here now? And this is like, it might not immediately jump into your head, but we have a carbon that has 1, 2, 3, 4 unique groups. A chiral center. Cool. So yes, now we have a chiral center. So racimization, you need a chiral alpha carbon with a hydrogen. So this is still the exact same reaction we did, still the same mechanism, nothing changed about like the mechanism. The only thing that changed is now we have a chiral center. So at this point, we're going to do like the backwards reaction. So if we were to go backwards instead of forwards, this H would come in, tack here, and move this back. That's a really ugly arrow. That back. So now we would get this again. But when we attack something, it has a chiral center, so we have to pay attention to stereochemistry. Would this add wedged or would it add dashed? I have a question. Saw your hand. No? Maybe I made that up. That's fine. Yes. I didn't see that. I'm about to draw them. I just want you guys to tell me if it's going to be wedged or dashed or both or neither. Both. Okay. So this one was kind of a tricky one, right? So why is it going to be both? So let's say I did give you wedged and dashed, right? In the beginning, it doesn't really matter because it could have started with whatever. But at this point, there's something important about the thing that's being attacked that I want you guys to notice. It's what? sp2, so that means it's planar. Yay. Okay. So this double bond is in fact planar. And that means we're going to get two products because there's no way we can specify attacking from the top or from the bottom. So we're going to get the wedged product. So we'll have ethyl methyl, and we'll also get mm-hmm. Oh yeah, it's not above the arrow. That's just my bad. It's it just is existing, but you're right. So it's meant to be here. I just redrew it so that you could see it attacking. Yes. Okay, so it's not that it stays like when you attack, right? You can either attack from the top or the bottom, but like when you have two groups sticking out, the rest of it is going to be like on the. So every time we have chirality, two groups are on the page, and then two groups are sticking out in either direction. So it's not necessarily like anything about the ethyl. It could have also been the methyl that stayed on the page. Just something had to stay. So this guy does not have a hydrogen because we took it away. The hydrogen is attacking and being added back. Yeah, so, okay. The way this is supposed to, like, it makes sense in my head, but I guess I didn't explain it, and you guys aren't in my head. So the red is one mechanism, and then the purple is like the backwards mechanism. So this is entirely separate from this. Like, this step isn't happening when we go backwards. That's the forward step. Yep. Make more sense? Okay, cool. Yes. Yes. You're welcome. I drew it really ugly, but yes. It could be an aldehyde. It just needs to have at least one alpha carbon. In all of chemistry, yes, but in this class, we're just gonna do aldehydes and ketones for the purposes of this class. That was a really good question. So just to reiterate, in case anyone didn't hear, we can use aldehydes or ketones for this chapter. It just needs to have at least one alpha carbon with a hydrogen. All right. So the last point for this reaction is if we can't differentiate between those two products, one of them is going to be the R, one of them is going to be the S. We're not going to do R and S right now. That's order one stuff. I lost where I was going. Oh yeah, if we have R and S in the product and we have no way of controlling which one we make more of, what is this going to be called? Something mixed. Yes, a racemic mixture. And that's why this reaction is called a racimization, because we make a racemic mixture. The aldehyde or ketone thing. So we could use either an aldehyde or a ketone as long as it has a chiral alpha carbon with a hydrogen. And it's kind of like the same idea for this whole chapter. It doesn't have to be chiral for everything else, but you could have an aldehyde or a ketone. It just needs to have an alpha carbon with a hydrogen. Okay, so like I said, this tends to be where I lose people. Is this okay? I don't want to move on if anyone's like super confused. So we do make the enol, right, as a product, but what we care more about is going backwards and getting the ketone. So technically it is an enol at the end, but we want to go backwards. Yep. I don't know why they act as if this is another reaction. It's not. You just have to know that if you specifically are doing a tautomerization with a chiral alpha carbon, you're going to make a racemic mixture when you go backwards. Yes. Not necessarily. It could have been just one. It could have been racemic, I mean, but it's usually just going to be one or the other. I didn't draw wedges and dashes, but because I wanted you guys to guess like the word chiral. But Dr. West will usually give you wedges. Yep. 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 So you first and then you. Okay, so we're always going forwards and backwards, right? So this reaction is going forward and backwards, but you only make a racemic mixture if you have a chiral center. So therefore, it's only considered a racimization if you have a chiral alpha carbon. It's just a ketone. It's just back to a tautomerization. So think of it this way. The umbrella term is tautomerization, and one specific category of it is a racimization. Because in that specific condition, you make a racemic mixture. Saw another hand. Okay, cool. You guys are asking such great questions. All right. Let me just right quick. Yes, okay. So the example question / practice question that I have for you guys is, which of the following would undergo racimization? So I'm going to give you guys a couple seconds to look at it, think about it, and then we're going to talk about it together. Are we ready to go over it? Does anyone want more time? Getting a lot of stares, so I'm guessing we can. So before I say anything, what do you guys think? Ooh. Okay. So even better, I love when you guys give me different answers because then I get to ask, why did you say what you said? So I heard someone say B and D. I don't know who it was. Okay, why do you think that? So I heard a couple people say, ooh. Why do you say ooh? Yes. Yeah, so what do we call that if there's two hydrogens and two unique groups? A prochiral center. So yes, we talked about that earlier this semester. So when we have two hydrogens, it's prochiral, but it's not chiral yet. So the first thing I would do is actually get rid of B and D because both of them have two or more hydrogens on either alpha carbon. So there. Now I heard a couple people say A and I heard a couple people say C. Does anyone want to explain? Yes. Perfect. So A and C are both chiral, but she said it perfectly. C is the only one that has this H present, and you have to have the hydrogen present. So that would be our correct answer. Sometimes Dr. West will straight up just like take B and D and just put both H's with a wedge and a dash to kind of trick you. So pay attention to that. Who wants to be my lovely assistant? I do got stickers, yes. Come on up, Eric. Okay, so I'm going to give you a marker and I want you to please draw the two resonance structures of the phenolate. Rest fell out, just let it happen. Yes. So there's two different forms of it. No, but you can phone a friend. Not show you, have them explain it to you. Okay. We have one kind person in the audience. Okay, so I'm going to draw on here what you guys are saying. Okay, so what else do we have to fill in? If it's an enolate, the negative. And then you have one more negative. Well, that's the resonance structure. So we had to put that negative charge on the O from somewhere, right? Oh. Yay! Perfect. Okay, here's your sticker. Vibe of today, the flying sloth that's sleeping. And then I have stickers for the two of you. I'll give it to you at the end. Negative. So big yay. So how are we feeling? Valid. Okay. So I'm gonna zoom out a tad so we can try and get as much on the page. Oh, actually, first, we're gonna skip this question until I see what Dr. West says in class today because I had some quarrels in the past. So for now, we're just gonna put an X by it and skip it. And let's see if there's any other. No. All right, so let's review. I'm actually gonna blank the screen. So, what is a tautomer? Yes, exactly. So there are two isomers that can interconvert an acid or base. What's a resonance structure? Like, what are a pair of resonance structures? When you move electrons, yes, it doesn't have to necessarily be a lone pair, but yes. So what is required to do an enolate chemistry reaction? Okay, so acid or base, exactly, but we need an alpha carbon that specifically has a hydrogen. Cool. And then if we're doing a racimization, you need a chiral center specifically on the alpha carbon. Cool. Yay. You guys did great today. Okay. I lied. Stay one more second. For flavor. Well, oh, that's a good point. I can do my hours for last week. Ta-da! Hello. Okay, I saw your email. Okay, I did want to talk to you about it. So I was gonna say yes, absolutely. The only thing is the person hasn't gotten back to me yet about the Princeton book. And so I just want to give him Yes. So the yeah. And I do have to be my parking lot. So feel free to scroll wherever you like. Yes. Yes, and I would just say here, Pirate Center has to have a hydrogen present. Okay.
I mean, it could be.
Yeah, so just describing like the backwards. Yep. I have not seen it, so I will ask about it in, well, in the. But so that one's tricky because technically they're both going to be equally substituted. I don't think you have to worry about that. It's only going to be one side. But if you had any other tautomerization, you would pick the most substitute side. Yes. Question or just join your sticker?